on campus. We're over in the Mine Minerals building across from ChemPhys on Rose Street. I'm also an adjunct professor in Earth and Environmental Sciences. So I was asked today to come in and talk to you about the geology underneath the plants and the bugs and everything else that you've been looking at in the bluegrass region. So I'm going to give a little overview of the rocks and the rock layering in central Kentucky and how that influences various aspects of the environment. And we'll also be talking a little bit about water resources, how the water moves in central Kentucky versus in other areas. And that's really going to be what the focus of our field trip will be. So we will be looking at sinking streams and sinkholes and things like that. And that's a very typical aspect of central Kentucky geology. So whenever you're looking at a landscape, obviously that landscape is a function of several things. And one of those things is the rock that's underneath it. And that rock changes as you go across Kentucky, and that results in many different types of landscapes. Also has a good record of the history of the state. And it influences agriculture, it influences where we can get natural resources for building supplies, for industrial development. It influences how much water is availability, what kind of water is there. And then obviously there's natural hazards. We just had a hurricane this weekend. So different slopes respond to water differently. Flooding is different in different areas depending on how much water falls. That all has something to do with the bedrock that's underneath. Okay, so you probably see, I know you've seen this map already. So this is the ecoregions map. This is a simplified physiographic map. And there's this area along the outside that's called the knobs. It's a series of hills. Everything inside that is relatively level or kind of rolling hills, and we call that the bluegrass. Okay? This is not in the notes, I just added this one, but just to show you, it's not just people making colors on a map, there's actually a basis for it. So this is air photos, and you can see this kind of dark rim. That's the knobs, lighter colored region inside what we call the bluegrass. This is LIDAR. Kentucky's pretty fortunate that we have the state covered by LIDAR. So this is through the vegetation, you're just seeing the land surface underneath that. And again, you see this distinct ring. You see a couple of other little different shapes inside. That's telling you there's differences in the bedrock underneath the vegetation. There's just the bluegrass region there. So this is a geologic map. And this geologic map is large groupings of different kind of rock represent the different colors that are on here. And the bluegrass region is this kind of purple color, the blue color, and about half this red color here. The line actually runs through this little red line here. And these are different ages of rocks, and they're different types of rocks. And if you look at the geologic map, the physiographic map, the ecoregions map, you can see there's gross similarities to the shapes of the regions. The overall shapes of the regions are largely controlled by the rocks that are underneath it. That's partly because soils are a function of bedrock, water, and plants. So part of that is the rock and the way the water moves through the rock. Okay? So in most areas, the geology is going to influence what the physiography, the topography shape, and the ecoregions, the types of plants that grow on those, have to do with each other. And so for geologic purposes, the bluegrass is the area of Ordovician rocks, Silurian rocks, and about half the Devonian rocks. There's a big difference in the Devonian between some limestones at the bottom and some shales at the top that make a change in the topography. Okay? And we'll talk about that here. All right, not sure I have that. All right, so if you take a line across the state like you were slicing across it, we're going to look at a simplified cross-section. And so geologists like to know what's happening under the ground. All of these rocks are sedimentary rocks. Anybody, how do sedimentary rocks form? Pressure. There's a little bit of pressure, but from sediment. All right, so you lay down sediment in layers. All right, flat layers. If nothing ever happened to them, you just have flat layers, piled one on top of the other, and you'd have the same thing at the top. That's never the way it is. All right, so we end up with different rocks at the surface, so something must have happened to those layers through time to create these different patterns on the surface. And what we're going to do is slice through the state, look at the rocks underneath to figure out why that happens. All right, so this is a cross section, very simplified, going down about 3,000 feet. This is the surface, going out here to Pine Mountain. Here we are in central Kentucky, Mississippi over there. And what you see is, in the center of the state, we have older rocks. Rocks at the bottom are older, rocks at the top are younger, laid down one on top of each other. So older rocks are at the surface along this thing we call the Cincinnati Arch. And it's kind of a hinge line that extends from north of Cincinnati down to Nashville. And so we have these Ordovician rocks all along that hinge line. On either side of it, we have basins, places where the earth dropped down through time. So we have the Appalachian Basin on one side in the east. We have what we call the Illinois Basin on the other side in the west. So we have this arch in the middle that brings older rocks to the surface. We have these big drop downs, depression, basically geologic depressions through time that sediment got filled in with younger rocks. So for example, the coal fields are in this dark blue-gray color here. That's where the coal-bearing rocks are, Pennsylvanian age. We don't have them in central Kentucky, so no coal here. So the overall distribution of the rock layers has a lot to do with the topography and the natural resources that are available as well. There's some texts that call this an uplift. It's not so much an uplift as a hinge. Okay? And then you'll see these lines. These are faults. Kentucky has a lot of faults. Ba-dum-bum. These faults aren't, the ones that are here in eastern and central Kentucky aren't active anymore that much. Obviously we have some faults out in the Mississippi embayment around New Madrid that are still very active. Those faults are places where the earth has moved up and down. All right, so that also influences what rocks are at the surface in any one spot. And they,
How do you make this map?
All right, so this map is made, we have tens of thousands of drill holes into the subsurface. All right, so we have wells that go down 15,000 feet. Most wells probably only go down about 5,000 feet. And they're all over Kentucky. And that's part of our job, is to keep a record of those, and then we correlate the rock units beneath the surface, and also some of the rock properties beneath the surface. So this is very generalized, but we have real detailed sections. And I'll tell you the other thing that's great about living in Kentucky, so we have the surface very accurately mapped. I'll talk about that in a second, more ways than most people do, most states do. We also have all this data available on the subsurface for free online. So a lot of places charge for subsurface data and things, but we try to make that all accessible. So it's very useful for a variety of purposes. But it gives us a pretty good understanding of what's happening in the subsurface. So sedimentary rock layers, faults and folds that are basically controlling the broad regional scale. Some faults that are controlling little local scale differences, and I'll show you some of those. And then at one time, some of these rocks went over, but we've had millions of years of erosion that have sliced down through. So if you think about layers, and you folded them up, and then you truncated them down, you'd end up with the pattern at the surface that's the geologic map. Okay? And that's true of geology in any way, right? Now these rocks are a record of the Earth history. All right, so when we use terms like Ordovician, Silurian, Devonian, Mississippian, those are age terms. All right, they're periods and systems of time that geologists classify rocks by. And in the bluegrass region, in the center here, we have mostly these Ordovician age rocks, which are in about 450 million years old, Silurian, and some of the Devonian. So that's the package of rocks. There's nowhere on Earth where the strata stack up completely everywhere with a complete record of Earth history. It's like pages of books that are missing. Erosion's going on all the time, weathering's going on. So you have these kind of gaps through time. All right? And then in Kentucky, we have a huge gap. We're missing all this. And then at the surface, is the sediment that we see. Most of that is from the last ice age to the modern. So we have near surface stuff, sediment that hasn't become rock, and then we have really old stuff that is rock. Four types of rock you can see in the bluegrass. All right, the most common one is limestone. Almost all the rocks you'd see in Lexington, all the stones on campus that are natural from here, all the walkways and stuff are made out of limestone. It's that gray to gray blue, relatively solid rock. It can be thin bedded or thick bedded. It's made out of calcium carbonate, which is calcium and oxygen and carbon. Okay. There's another type of rock. It's more common on the edges. It occurs towards the eastern Kentucky edge of the bluegrass, and it's also in the Louisville area a lot, is dolomite. We sometimes call dolomite dolostone because there is a mineral dolomite that the rock dolomite is composed of. So to make it a little less confusing, sometimes we call that dolostone to say you're talking about the rock versus the mineral. It looks like a limestone to somebody that's not a geologist. It has a little bit more of a sugary texture, tends to have less fossils in it than a limestone would. But they're both pretty solid rocks made out of carbonate. Dolomite has a little more magnesium in it. All right, so these two rocks have a lot of carbonate in them. And that influences how easily they erode with acids and things that are slightly acidic. Shale is a real thin-bedded laminated rock that's not made out of carbonate most of the time. There are some shales that are made out of carbonate. Most of the ones on the edges of the coal field are more silica-based. But because it's so thin-bedded and it's originally made from mud, it breaks down really easy. All right, so it has a kind of different resistance to erosion and weathering than limestone and dolomite do. And then we have a little bit of siltstone. There's not a lot of siltstone. There's a unit called the Garrod siltstone that occurs in the Ordovician. It's just made out of silt grains. It's a little bit more sturdy than a shale. And in sedimentary rocks, you have rocks that are kind of chemically precipitated or a mix of chemical and physical precipitation. That's mostly the carbonates. And then you have ones that are made out of grains that are physically moved and deposited, and that's shale, siltstone, sandstone, conglomerate. Sandstone just means it's made out of sand grains. Conglomerate means it's made out of pebbles. And we don't have any sandstone or conglomerate in central Kentucky. Okay, so mostly limestone and dolomite with a little bit of shale mixed in. And how that relates, this picture isn't in the notes, but just for a general picture, how that relates to topography in the physiographic regions is when you have thick beds of units, or they're very thick limestone or dolomite, it tends to be pretty resistant. Okay, it's not going to erode as easily as something that's a shale. So this is an interbed of shale, and if you're driving down the highway and you see something that's flat in central Kentucky and then you see kind of a reentrant, that reentrant is almost always going to be a little shale body. If you have thicker shales, you can kind of guess that those would make a different kind of slope than a thicker limestone or a thicker dolomite. Right? So the ratio of dolomite and limestone to shale has a lot to do with how easily the surface is going to weather. It also has a little bit to do with what kind of soils are going to form and how easily plant roots are going to get down into the material. Okay? And we'll see examples of these on the field trip. All right, so to break down a little bit further, this is the ecoregions map and some of the subdivisions of the ecoregions. So you have the inner bluegrass, pretty much in the Lexington area here. Then you have this subdivision called the hills of the bluegrass, and then you have the outer bluegrass, and then it's bordered by the knobs area, which is a different region. If you compare that to a more detailed geology map, this green area here is the Lexington limestone. It's relatively thick-bedded limestone. When you get to the edges of that, you're starting to get units on top that have more shale in them. All right, so here's the inner bluegrass. Here's the Lexington limestone. Then you have this area out here that's got things called the Clays Ferry and Cope Formation. And those two units are something like 75 to 100 feet of shale with thin limestones in them. All right, so it's a different rock type, and it leads to slightly different physiographic and ecoregions. You get outside of that, and you have kind of a mix of limestones and shales, a series of different beds going out to the edges, and that's where the outer bluegrass is, and it's kind of a mix of these two other regions. Also, I talked about faults a little bit earlier. These black lines are faults. This is the Lexington fault system. Here's another fault system here. And you can see along this one, there's a very sharp change across the ecoregion boundaries and across the geology boundaries, because that fault is bringing different rocks to the surface right at that area, rather than kind of a more gradational change sideways. So some of the sharp lines, especially down in here, in the ecoregions are related to sharp offsets of rock types on the geology map underneath. And I wanted to show some of the topographic views of what those look like. And I'm going to show you later in the class how to get on the website if you haven't seen it, but you can zoom into any area and see aerial photos or LiDAR. This is LiDAR images of just examples of what the inner bluegrass, the hills of the bluegrass, and the outer bluegrass are like. This is I-64 north of Lexington, and you see these little depressions here. Those are sinkholes. All right. There's not much topography here. It's level land, level horse farms. Okay, that's pretty typical of the inner bluegrass where you have this thick limestone underneath. And you go to the hills of the bluegrass, and you can see this big difference in what the topography looks like. You have a really dissected topography. There's lots of little drainages and little creeks and things in here. All right, that's because you have this thick shale. And that thick shale is just weathering really easy. It's eroding really easy. All right. Some places there'll be a limestone cap rock at the top that holds up some of the hills, or makes a little broader plateau on some of the hills. But there's a direct relationship between the difference in these two landscapes that's based on the rock types underneath. And then when you get out to the outer bluegrass, and this is just an example, I think this is the Gene Snyder in I-64, and you've got kind of a mix. You've got some relief on some of the places where there's a little bit more shale in the rocks. And then here's a big limestone that's got some sinkholes in it. All right, so you kind of are going back and forth between the two. But just making the case and kind of showing visually how the rocks are influencing the topography. Part of that topographic difference, especially in the bluegrass, has to do with how water moves. And water is moving both on the surface and water is moving in the ground. So in central Kentucky, where we have limestones, and in the outer bluegrass, where we have a mix of limestones and shales, those form what we call a karst landscape or a karst terrain. And karst is any place you have a lot of springs and caves, sinkholes. All right? And what it usually means is that instead of a lot of water being transported on the surface, the water is going down into the ground. So in central Kentucky, we have a much lower density of surface streams than you do in, for example, eastern Kentucky or western Kentucky. It's because a lot of our water goes into the ground. And that's because we have this limestone bedrock. So we have limestone as a bedrock. Limestone is very susceptible to water moving in, making conduits, and making caves. When you're in that hills region, where you have the shale as the bedrock, no karst. So you have lots of streams and you have lots of erosion. You get out into the outer bluegrass, it's a mix between the two. All right. So the carbonate dissolves with just a little bit of acid. So the acids that are in roots from trees, those can cause some dissolving. Acids that come in some rainwaters, acids that come in some surface waters, acid comes from decays of plant materials. That all acts through time to erode down and make this kind of karst terrain. We will see on the field trip spring something called a karst window, which just means you get to see the underlying karst because there's a sinkhole. We will see a sinking stream, and we'll see a swallow hole. Okay, so we'll see examples in the field of what those look like. This is a map where geologists have basically taken the rock units that they know are at the surface and made a susceptibility to karst. So it's basically a karst potential map. So the areas that's in dark blue, those have a high potential for karst. There's lots of sinkholes and lots of sinking streams. Areas that are in white have almost no potential. Areas that are light blue, mix. All right. If you think about it, that has a lot to do with your water supply. It has a lot to do with your environmental issues that are around water. So water traveling underground, it's a lot harder sometimes to see where it's going and to track what's going into it than water that's at the surface. If you're looking for water supplies, do you have a surface stream that you can rely on, or do you need to put wells underground? If you're putting wells underground, unless you hit a conduit or a cave, you're not going to get any water. It's only where you hit a conduit or a cave that has water traveling through it that you're going to hit some water. All right, so you can have people in central Kentucky that put wells down 15, 20 feet away from each other, and one will be dry and one will be wet. It's very different than putting wells down in something in the Ohio River floodplain, where every place you put it down, you're going to get water. So there's very different water issues in central Kentucky than there is in some of the regions off to the side. Just a quick little Earth history. All right, so those rock units contain fossils. They contain different types of bedding that tells us how that rock was deposited, so we can look through time. It's what has happened in ancient Kentucky to get us the rocks we have, and then look closer in time. For geologists, we throw around millions of years as like it's nothing, but closer in time to get to how the landscape is actually formed. So if you remember this map, this little cross section, the oldest rocks are at the surface of Kentucky, and the oldest rocks are actually whatever the lowest water level is in the Kentucky River down the Clays Ferry. So we know that's the oldest rocks come into the surface, or actually Camp Nelson, not Clays Ferry. This is called the Camp Nelson Formation. It's Ordovician age, about 455 million years ago. And these were tidal flats under a shallow marine sea. So we know Kentucky was covered by an ocean at that time. This is just pictures around central Kentucky, lots of limestone and shale, lots of karst features. Most of the horse farms, you'll see areas where there's a little circular fence with a depression in it and some trees growing out of it. Those are sinkholes. We do have this river, big river that runs through the center and it is entrenched into the Palisades. We'll talk about that in a second. And then lots of springs. It's McConnell Springs. We'll see that on Friday. Lots of fossils. In fact, I'm from Illinois originally. I grew up in Chicago. I went to the University of Illinois. We came down here fossil collecting on a field trip. Tons of fossils. And the state fossil is a brachiopod. So lots of places you can collect the state fossil right here in central Kentucky. But they tell us this area used to be covered by a sea. Silurian rocks are somewhat similar, so lots of limestone, lots of shale. You also get some dolomite. That's this kind of orangish to whitish limestone. And this is actually the contact between the top of the Devonian and the black shale that forms the knobs. So you can kind of see resistant rock, and then this is weathering real easy, and it's going to make a hill slope called that typifies the knobs region. Devonian rocks, lots of Devonian rocks on that outer rim here. In the middle part of the Devonian is all limestone. This is the Falls of the Ohio at Louisville. It's a International World Historic Site. Lots of fossils there. Again, more underwater life. Actually, coral mounds, big coral sea at that time. We're going to include, this is the knobs. So this is what the topography outside the bluegrass looks like. It's what makes the border of the bluegrass. And it's upper Devonian, mostly black shales. These really dark shales. Fracture real easy, weather down real easy. And every place there's a knob like this. Whoops, my poker's not working. There's a resistant rock up at the top that's holding up the slope. If you don't have that resistant rock at the top, you end up getting flat on the sides and then going out into the flatter rocks of the bluegrass. Then we have this big gap in time, and then we have the ice ages. And the ice ages are actually multiple retreats and regressions of ice sheets across the northern latitudes. And the farthest one gets down to just around the Ohio River. The Ohio River wasn't there before the ice ages. The major drainage went up this way. It was called the Taze River. We have remnants of it that are left, but as you can imagine, as that ice moves back and forth, it erodes and changes all the drainages in its path. All the rivers and tributaries that are going into those streams also have to change and adjust to the new topography and the new drainages. So once the Ohio River drainage starts from the melting here, all the rivers in Kentucky have to adjust their drainages. And one of those adjustments is erosion down to make the Palisades. Okay? So we do have, if you've ever driven north, we do have a couple of ice age things in the ice age sediments in the Ohio River Valley. But the biggest thing you'll see in topography and landscape difference is if you drive either from Cincinnati north or